Okay, so hello and welcome again to our video lecture. So welcome again to Principles of Reinforced Concrete. And in today's video lecture, we would be discussing about Section 425 of NSCP 2015, and that discusses about reinforcement detail. So after designing your structural member in reinforced concrete, may that be in shear, in flexure, in axial, or whatever structural behavior that you have designed your reinforced concrete member, you will now draw them in plans. So we will now draw them in structural plans that will be interpreted soon in construction sites. But before drawing, you must of course detail them first. Thus, yun, reinforcement detail. So that is what we would be discussing about in this video lecture. So for the majority of these provisions, they are to be formula based. And since they are to be formula based, you will be solving them via direct substitution. So very basic, except for one provision here. So anyway, so let's say that you want to know the detail or the detail provision by NSCP when we are to discuss about minimum spacing. So actually guys, we have already discussed about this in the previous video lecture when we were still designing, no? So suppose that this is what our structural member would look like. So let's say that this is to be a beam. So of course, when you have your beams, since it is to be a flexural member, you must have your steel in longitudinal direction. So these are to be the longitudinal bars, and these bars are concerned with flexure or with moment. So these are to be it. And since it is once again a beam, so this is to be a beam which is to be subjected with transverse loads. So here, of course, it is also subject to shear. Thus, we must also design its shear reinforcement. And in this case, guys, so looking at the figure to your right. So by the way, guys, I got this figure in this website, theconstructor.org. So I do not own this photo. Anyway, so once again, this member is to be subjected with shear. Thus, we must also provide shear reinforcement. And shear reinforcement, these are to be it. So this members right here, or this, well, square reinforcements here. So these are to be what you would be calling your stirrups. So stirrups. So shear stirrups. So these are to be for your beams. And the shear reinforcement for your columns are what you would be calling your lateral ties. So the difference between shear stirrups and lateral ties is that shear stirrups is for your flexure beams and lateral ties are for your columns. So yun lang naman pinagkaiba nila. Okay, so moving forward, so what we were discussing about earlier was the minimum spacing. So your minimum spacing is actually the clear spacing between your rebars. So it would be this distance here, this distance here, and etc. And once again, we have already discussed about this before in section 425.2. So by the way, guys, this is to be a typographical error from NSCP. This should be 25 mm. Okay, so with that, guys, so for your spacing here, this spacing shall not be greater than 25 mm. So which is to be this, the diameter of the rebar, and 4/3 the maximum size of the aggregates, or 4/3 DAGG. So ayan lang yon. Direct substitution or just compare it with whatever spacing that you have solved here, and ayun, that is to be for the first provision. So for the next provisions here, they are actually once again formula based. So when I say formula based, direct substitution, input what is known, then there. So for example, that we want to know the standard hook, seismic hooks and cross ties, I should say. I'm sorry. So, ayon, we would just be going to this provision. So, 425.3. And once again, ulitin ko lang, they are to be formula-based. So, suppose that these are to be the bends. So, I will just be increasing our table here. So, this table, which is to be table 425.3.2, talks about the minimum inside bend diameters for standard hook geometry for stirrup, ties, and hoops. So these are to be for your shear reinforcement. All of this. So once again, if you would be looking at our section here, we have here your stirrups. And as you can see, your stirrups, the section for your stirrups would look like this. So meron tayong rebars. So these are to be your longitudinal bars. And they are to be surrounded by, let's say, your, of course, your stirrups. So ito yung stirrups natin. And of course, you would be bending them. So this bends right here. So meron tayong bend at this part, this part, this part, and this part. So if you want to know the provisions of those bends, just go to this table. And for those provisions, they are to be dependent upon the diameter of the rebar that you have chosen for your shear reinforcement. So for example, that you have chosen a 10 mm diameter rebar, you would just be using these provisions. So for the minimum inside bend diameter, that is just 4 times diameter of the rebar. So once again, if you have used 10 mm, so 4 times 10 mm, that is to be 40 mm. So that is to be the minimum inside bend diameter. So ano ba tong minimum inside bend diameter? So minimum inside bend diameter is to be this diameter. So it is to be a imaginary circle here in such a way that if you would be bending your rebars, the diameter of this, the diameter of this arc, so this would now result to be an arc, and that, this should be 40 mm diameter, this imaginary circle right here. So basic. And another thing, if you would be, of course, you would be extending them. So the minimum extension here is to be greater than, oops, I think this is to be a typographical error. So nakalagay dito 46B. So I think this is to be 6 diameter B, or maybe 4 diameter B. But in my case, guys, I would just be using 6 diameter B, or 6 diameter of bar, since this is to be much more conservative. So hindi ko alam kung na-update na to ng NSCP, but this is to be erroneous. So it is either 4 dB or 6 dB, but of course this would give you a higher value, and thus it will be much more conservative. So ayun, in that case, guys, so let's say 6 diameter rebar. So 6 times 10, this is to be 60 mm. So whichever is greater than 75 mm and 60 mm would be your extension here. So in this case, 75 mm. Ito yung mag-govern. So mali itong 60 mm. Okay, so that is for your 90-degree hook. But what about for your 135-degree hook? And in this case, guys, so as you can see, this image here, so I would just be increasing the image size. So as you can see at this part, so we have hooks here. So meron tayong hook dito, and these hooks are to be 135 degrees. Okay, so with that, guys, you will be using this provision. And once again, direct substitution. If you are using 10 mm, you will be making use of this provision, and this figure as a reference. So napaka-basic niyan. So with that, guys, I will just be moving forward with the other provisions here. So next, development of reinforcement. So ayun, guys, we would be mainly focusing on the development of reinforcement, because once again, this provision is to be formula-based, and all of these are formula-based. And besides, for your splices, they are to be dependent upon your development length. So your splices is, well, tsaka na natin pag-usapan yan. So what is to be the development of reinforcement? Okay, so when we say development of reinforcement, which is to be this, we are to talk about the development length LD. So LD is to be our main variable in this section. So when we say development length is actually the length of embedment between two concrete members to establish adequate bond strength. So if I am to draw a figure here, so let's say that we have a reinforced concrete column. And let's say, of course, if you have your column, of course, you have your beams. So let's say that you have your beams here. And previously, we have decided our beams already, and let's say that at this particular section, you will be having rebars here at the top. So these are to be for your tension reinforcement. And let's say that you have your compression reinforcement at this portion. Okay, so once again, your development length is to be the embedment length for, to ensure adequate bondage between your column and your beam. So with that, guys, of course, you would now be extending this to whatever provision that is provided. So let's say that it is to be extended in this manner. And for your compression steel bars, let's say that it is to be embedded in this manner. Because let's say that if you wouldn't be providing this, and well, by common sense, of course, this would fall because of course it would not be embedded. So if you are to look at this particular figure from Quora.com, so once again, I do not own these photos. Let's say that you have designed your rebars in this manner. So you have your top bars and your bottom bars, and if you would not be extending them in your columns, this part will now fall. So this is now to be your critical section here. So once again, this would now be destroyed and your beam would now fall. So what you will be doing is that you will be embedding them in this manner. Thus, you now have your value for your LD. So your LD is to be the length or the development length that is to be embedded between the two structural members that you are designing, or yun. So in three-dimensional view or in, let's say, real-time view, it is to be like this. So as you can see, the top bars were extended as well as for the bottom bars. Okay, so that is for your LD. So for the minimum development length, they are also formula based, and you can actually solve for them using section 425.4.2.2 or 425.4.2.3. So whichever is greater between those two and 300 mm. Oh, by the way, guys, it is indicated here or. So let's say that you have chosen this provision, you do not need to solve for this provision any longer. Or let's say that you have chosen these formulas, you do not need to solve for this formula any longer. Kasi nga, or yan. Okay, so going to that table, so that is, this is to be table 425.4.2.2. Then as you can see, they are formula based once again. So direct substitution, substitute known values, then you will now be solving for LD minimum already. So that is 425.4.2.2, and this is to be 425.4.2.3. So once again, you do not need to solve for them. So to solve for this provision and solve for this provision. So you can just choose one provision here. And in my case, I would be choosing this table. So I would be choosing this because as you can see in this provision, there are plenty of variables. So ang daming solve, masyado matrabaho. And with that, I will be choosing this. So this is to be our content for our video for today. And as you can see, so I will just be increasing the size here. The table size. So as you can see at this part, the formula for this particular section is Fy times psi t. So I think this is to be the Greek letter psi, yung tinidor ni Judas. Teka nga, I will just be checking it in Google. Okay, so I am right. Di ko lang naipakita dito sa video. Nag-Google ako on the side. This is to be for your Greek letter psi. Okay, so we have here your psi t, psi e. You also have here your lambda. So this lambda here. And you are also, it is also included here the familiar variables Fy, and this is to be your yield stress for your steel, and F prime C. So this is to be the compressive strength of your concrete. And your dB is to be the bar diameter. Okay, so what are to be these variables? So we have here your psi t, psi e, and lambda. So they are to be given in this table. So it may be this one or it may be this one. So that may be for 25.4.2.4 or 4.5.4.3.2. So in this case, guys, these are to be the modification factors for development of deformed wires, deformed bars or deformed wires in tension. So let's say that these are to be for your tension reinforcement. You will now be making use of this particular table. Okay, so let's have an example for you to understand it better. So for a moment. Okay, so for our illustrative example here, so this beam right here is already familiar to you if you have already watched our previous video lectures. So this was the beam or the continuous beam that we have solved via simplified method. And this is to be the beam that we have designed in our design of singly reinforced beams. So these are to be the result of those. So these are to be its moments and these are to be its shear via simplified method. So do we need those values? Actually, yes, but let's discuss about that later. So once again, if let's say that we want to solve for the development lengths here, so let's say I want to solve for the development length in this part or at this section here. So let's solve for this, and let's say I want to solve for the midspan here for an example. And as for the others, you can solve for it at on your own because it is already repetitive. So kuha lang tayo ng mga examples dito. Let's say that this part and this part. So I would just be discussing about the development lengths. Okay, so going back to this formula. So once again, your minimum LD is to be either of these values here. And if you can remember from before when we have designed these beams here, we have used dB equal to 20 mm. So this was the bar diameters that we have used in the previous video lecture. So yun yung ginamit natin ngayon dito. So with that, guys, so if you would be looking at this table, it may either be this or this, but since our dB is to be equal to 20 mm, we would now be using this formula. So the question, will we use this or will we use this? So once again, it is to be dependent upon this provision. Okay, so let's say that if your clear spacing of bars or wires being developed or spliced is not less than dB, or let's say the clear cover is at least dB and stirrups or ties throughout is not to be less than the code minimum. So let's check for the first provision. So it is to be not less than dB. So if you can remember once again that when we have designed this members here, we have already taken this into consideration, which is to be the spacing. So we have already checked that it is to be adequate in all of this. And such, with such, no? So going back here, so we can say that it is to be not less than dB. So 20 mm yung dB natin. And the clear spacing SC is to be greater than 20 mm. So check. So the first one is already conforming. And the clear cover at least dB. So our dB once again is 20 mm and our concrete cover was 40 mm. So concrete cover once again was 40 mm plus the diameter of your shear stirrups, and that is to be plus to 10 mm. Thus, this is now to be 50 mm. Okay, so 50 mm. So with that, guys, this second provision is conforming. So the clear cover is at least dB. And stirrups or ties throughout dB should not be less than the code minimum. Though I did not design the shear reinforcement of our beam before, of course, if you would be designing it, it should not be less than the code minimum. So if you have designed your shear reinforcement properly, this shouldn't be an issue any longer. So with that, guys, we will now be using this formula. So by the way guys, we also have another provision here, and since it is indicated or here, if this is to be conforming already, I do not need to check this any longer. Because regardless if this is to be conforming or not, we can still use this kasi nga sabi dito or, not and. So it did not include here and, it is said here or. So once that this is already adequate or conforming, I do not need to check this any longer. But let's say that this is to be non-conforming, check for this first before concluding that you will be making use of this provision or this formula. But once again, this formula here is to be adequate already. Okay, so I will just be increasing the size here once again for you to see it better. So we would be making use of this provision once again, which is Fy times psi t times psi e divided by 2.1 times lambda times square root of Fc prime, the quantity times the diameter of the rebar. Okay, so what is to be for the value of our Fy? So by the way, isulat ko na nga lang dito. So wala tayong space. So let's just solve for them here. So I will just be copying this to our slide here. Okay. So what is to be the value for our Fy? So this should be given already. So our Fy is to be equal to 420 megapascals. So 420. And as for our F prime C, this is to be 28 megapascals. So megapascal, and this is also megapascal. And what else? What else do we need? So what is to be the value for your psi t? So psi t, psi e, and what else? dB. So for dB, the bar diameter that we have chosen here was 20 mm. So 20 mm, these are to be given. And as for your psi t, psi e, and lambda, so we would now be going back to our table here. And all of these tables are actually in your NSCP. So table 425.4.2.4. So for your lambda, this is to be the modification factor for the weight of your concrete. So in here, if your concrete is to be lightweight, the value for your lambda is 0.75. But since it is not included in our problem, it is safe to assume that our lambda is to be 1.0. And we will be assuming that our normal weight, that our concrete is to be normal in weight. So with that, our lambda, do we need that actually? Oh yeah. So for your lambda, this is to be 1.0. Okay, but what about for your psi t and psi e? So your psi e, so let's discuss about psi e first. This is to be if your steel rebars are to be coated in epoxy. So that may be 1.5, 1.2, or 1.0. And by the way guys, so for your epoxy, so let's say that these are to be your rebars. If you would now be painting your rebars with epoxy to, as a non-corrosive measure, so if corrosion is to be a main issue here, you must paint them in epoxy. However, if you would now be painting your rebars in epoxy, they would now be slippery. So, as compared if it is not to be coated. So, if your rebar is to be slippery, it is logical for you to increase the development length kasi nga madulas siya. So, ayun. But since in our problem, it is not indicated that it is to be epoxy coated, so we will be assuming here that once again, our rebar is to be non-coated or, uncoated. So, with that, our value for our psi e or our modification for epoxy is also 1.0. Okay. So moving forward, so what about for our psi t? So for our psi t or for our casting position, it is to be dependent upon this provision. So you would be using 1.3 if more than 300 mm of fresh concrete is placed below the horizontal reinforcement, and if not, 1.0. Okay, so let us check here. So in this section, guys. So I will just be copying this. So in this particular section, the total depth of it is to be 500 mm and the effective depth is to be 440 mm. So effective depth 440 mm. But take note, guys, that so if I would be increasing this here, the value for your D is to be measured from the centroid of your rebars here. So let's say that this is to be the centroid. This is to be 440. But as per indicated here, I mean for this provision, this is not to be the center to center spacing. This should be from the bottom of the rebar up until this point. So with that, if this is to be 20 mm and half of 20 mm is 10 mm, it means that this particular section here or this particular dimension here is to be equal to 430. So, or 440 minus 20 over 2. So 430. So is 430 greater than 300 mm? So short answer, yes. So meaning, we will be using 1.3 here. Okay, so with that, this is now to be equal to 1.3. Okay, so another thing which I did not discuss earlier. So we also have a provision here at this part. So for 5.5.4, we have a provision here saying that the value for your square root of Fc prime should not be greater than 8.3 megapascal. So since our Fc prime or our F prime C is to be 28 megapascal, our square root of 28 is to be equal to, so looking at the calculator to your left, so the square root of 28, this is to be equal to 5.29. So it is to be less than 8.3 megapascal. So we can use this actually. So if we are to check for the limit, no? So what is to be the value of your F prime C? If the limit is to be 8.3 megapascal, so solving for F prime C. By the way, this is just to be a segue. So hindi kasama to sa problem. I'm just explaining things. So 8.3 squared. This is to be 68.89 megapascal. So what that means is that if, let's say, your F prime C is to be beyond 68.89, you will use 8.3 megapascal for your square root of F prime C. But since this compressive strength is actually, it's not impossible, but it is very hard to attain because as you can see that our F prime C here is to be 28 megapascal, then that is not much of an issue. So this provision is not much of an issue. Oh, by the way, guys, we would not be introducing a reduction factor fee in the development lengths. So there. Okay. So moving forward, we also have a provision here actually that the product of psi t and psi e should not exceed 1.7. And since our psi e a while ago is 1.0 and psi t is 1.3, so 1.3 times 1.0, that is equal to 1.3. So it did not exceed 1.7. But for example that it exceeded 1.7, you will now use 1.7. So for example, so this is just for an example once again, that you have chosen 1.3 here and 1.5 here. So 1.3 times 1.5, this is to be equal to, so 1.3 times 1.5, that is to be equal to 1.95. And since it already exceeded 1.7, you will now use 1.7 as your sigma t times sigma e. But once again, that is not applicable to our work because we have chosen 1.0 and 1.3. Okay. So solving for what needs to be solved here. So for your minimum development length here, this is to be equal to, so Fy So looking at the calculator to your left, so Fy times lambda t. So by the way guys, I am just substituting this. I am just substituting all of these variables here to this equation. Okay, so 420 times psi t, or that is to be 1.3, times psi e, that is to be 1.0. Oops, I'm sorry. 1.3 times 1.0 divided by 2.1 times lambda, and our lambda is 1, times the square root of fc prime. So times square root of 28 times the diameter of bars, and that is to be 20. So 420 times 1.3 times 1 divided by 2.1 times lambda times square root of fc prime times 20. And this is to be equal to 982.71 mm. And if I am to be the one designing, since this is very hard to lay out, you can actually round them up to, let's say, LD is equal to 985, or let's say 990, or if you are to be the engineers very soon, you can actually use 1 meter in this case. Because once again, these are just to be the minimum. So minimum lang yan. So you can increase it, but you cannot decrease it. Okay, so the higher the development length, the safer it is, but of course, the less economical it is. Okay, so going back here, so in that case, if that is to be our minimum LD already, or the minimum development length, it means that, let's say, in this part, your development length should be 9.8 meters here. So 0.98 meters here, and 0.98 meters here, as well as for the other. So 0.98 meters as per the minimum provision, or the minimum development length. But the question is it already adequate? So is the minimum already adequate in our structure here? So we will now be checking. So just like in your raw minimum before, so when you have solved for your raw minimum, you still check for the raw required. So let's say that your raw required is to be less than your raw minimum would now govern. But let's say that your raw required is to be greater than your raw minimum, your raw required would now govern. Okay, so now with that, let us now solve for the theoretical cutoff point here. So that is to be our main topic here. Okay, and since we are to be solving for this section, so I will just be isolating this section. So I will just be copying this to another slide. Okay, so if I am to draw the shear moment diagram of this, it is now to be looking like this. So for the moment diagram, so negative 126.9, it is to be located here. Negative 238.29. And positive 145.0286. So 145.0286, negative 238.29, and this is to be negative 126.9. So its moment diagram would now practically look like this. So by the way guys, drawing tayo mas malaki. I'm sorry. So let's say that this is to be the the moment diagram once again. So let's say that this is to be your section, or your, by the way, your member. Of course, since this is to be a negative moment, the rebars should be on top. So these are to be your tension rebars. So if I am to copy this section once again, so this is what it would look like, by the way guys. So ayun, silitan nga natin para medyo skilled naman kahit papano. Okay, so it would now basically look like this. Okay, so what is to be this length? So as per the minimum, this is to be, so your LD is to be 0.98 something. So I forgot. So 0.9827 meters. Okay, so theoretically guys, if this is to be your let's say your rebars or the length of your rebars, this is to be your basis. Since this is to be your negative moment, it is logical for us to terminate the rebar at this point. Because from this point onwards, this is already a positive moment. And with that, the tension reinforcement is now located at the bottom part. So theoretically, that is to be the appeal. So ayun. However, in NSCP or in ACI, you must still you must still have an extension here as a factor of safety. So with that, guys, by the way, this is just to be your LD minimum. So LD minimum. So LD minimum. And let's say that this is to be for your LD bars M. And we also have our LD minimum for LDL later, but let's talk about that later. Anyway, so let's say that this is to be the theoretical location of your point of inflection. So let's say that this is to be your point of inflection. So when we see point of inflection, this is to be the point that is to be zero in moment. So kapag ganyan, guys, it is once again logical for us to terminate our development length at this point kasi nga hindi niya naman na kailangan throughout. But according to NSCP in this provision, so at this provision, you must have an extension here of D, 12 dB or ln over 16. So let's say that that is to be the point of inflection already. We must still increase it. So dagdag tayo as a factor of safety. So for your extension, so your extension here may either be D or 12 dB or ln over 16. Once that you will now be solving for this length here, just solve for this length here. So solve for this and add your extension. And after doing that, you will now be comparing it if it is to be greater than or less than your minimum. So if it is less than, you will now be making use of this. Okay, but take note, guys, that it is in the code that we can actually divide this into two. So if you want to, let's say, provide 3 rebars throughout. So since this is just to be a minimum, if you want to provide still rebars up until the end of the beam, it is okay. Theoretically, it is safe, but of course, it is not economical. So now it is, if we are to talk about economy, we can actually divide this into 2 cutoff points. So with that, guys, so as you can see, this is to be your section. So let's say that in this portion, we would be having your bars bar L, and we also have your bar M. So let's say that your bar M is to be the one on yellow. So with that, this is to be your bar M. So what is to be your bar L and your bar M? So drawing na nga lang tayo para di magulo. And these are to be your tension and these are to be for your compression. Okay, so for your bars M, so bars M and your bars L, so your bars M are to be the bars that will theoretically approach the point of inflection. So up until point of inflection, so theoretically. And your bars L is, well, it would not approach the point of inflection. So for your bars M, guys, so your bars M at least 1/3 of the area of the steel area. So this is just for tension, guys. So tension. And for your bars L, of course, what would remain? So remaining. So for example, that you have these 4 rebars which are to be in the same size. So as you can see, 4 rebars, 4 divided by 3, this is to be 1.333. So in this case, guys, if this is to be for your value for your M, so 1.33 rebars, but this is just to be the minimum. And with such, guys, we would now be increasing this to 2 pieces. So for your bars M, it is logical if you would now be choosing the exterior rebars. So with that, guys, ibahin natin yung color. So let's say that this is to be for your bars M. So this is for your bars M. And the remaining one is to be for your bars L. So this is now to be for your bars L. So what is to be the importance of me segregating both of these, so bars L and bars M? So in this section, guys, so let's go back here. So since, as you can see, we have here this section, so meaning that at the top portion, you would be having 3 rebars. So in this case, for your bars N, so bars, let's say M, this is to be 1/3 of the area. And 1/3, so 1/3 of, so how many rebars do we have here? So this is to be 3. So 1/3 times 3. So by the way, guys, I am just multiplying it by pieces because they have the same size. Pero pag magkakaiba yan ng size, so if they have different sizes, what you will be doing is that you will be getting 1/3 of the area. Okay, so moving forward, so our answer here is to be 1. But the thing is, guys, if we would just be extending 1 up until the point of inflection, medyo di naman maganda yon. So with that, guys, I can say that for your M here, since from our provision that I have stated here, it is to be at least 1/3, so we can actually increase. So let us just set that the minimum M is to be 2 pieces. So with that, 2 pieces. Okay, so since that is to be 2 pieces, so for the value for your L, what remains? So 3 minus 2, and that is now to be equal to 1. Okay, so with such, guys, so if this is to be our section, let's say that I will be coloring our L blue. So L is equal to 1 piece. So I will just be recoloring this. So for example, that this is to be your bars M, which are to be the ones in green. So delete lang natin itong mga red na to. And for your bar L, that is to be for your blue. So this is to be for your bar L. So this is to be for your bars M, which is to be the one in green. So bars M. And the one at the middle, let's say that this is to be for your bars L. Okay, so let's say that this is to be the face of your support. So for your bars M, it should be reaching this point if this is to be your point of inflection, because at this section here, this is already a positive moment, so meaning that the tension reinforcement should be at the bottom part already. So up until there, theoretically, that according to the code, we will be extending this by little. So we will be extending that. So this E here is equal to, so what is to be the greater than D, or this is to be the effective depth of the section. D, so okay. So this, so D 12 dB and or ln over 16, whichever is greater. So that is just for the extension. Okay, so there. So once again, the bars M would now be reaching that point. So if you want your 3 bars to go here, all your 3 bars to have this length. So let's say that all your bars M and L would be reaching this point. So theoretically, no problem, but that would be not economical. So we would now be segregating them into 2 lengths. So for your bars L, we can actually cut it somewhere here. So let's say this part here. So for your bars L, it can actually just stop here. So ito yung bars L natin. So there. theoretically. But once again, we must once again introduce another extension. So for your extension, guys, so extension, same, that may be D or 12 dB or ln over 16. Oops, I'm sorry. So this should not be included, by the way. So it should be just D or 12 dB. So bakit hindi natin sinama yung ln over 16? Because if we would be going back to this provision, it is said here that at least 1/3 of the negative reinforcement. And if you are to talk about this, so 1/3 of the negative moment. So ito, guys, ano lang to? This is just for bars M. So for your bars L, just remove this. So this is just for your bars L. Okay. So going back here. So ayun, so what we would be doing here is that we will now be checking for this location for your bars L and this location for your bars M. Okay, so if I am to redraw this at a much simpler one, so for its moment diagram, kailan drawing na ako. So once again, this is to be the negative moment. And let's say that I am just to draw this part only. So I am just to draw this part only. So with that, it would now look like this. Whereas the value here is to be negative 126.9 kilonewton meter. So now we would now be solving for both this location and this location. So once again, if I am to draw its section here. So I'm sorry, dami ko na na-drawing na section. It's just that ang pangit ko mag-drawing dito digitally. So for your bars M, it should be this part. And for your bars L, it should be this part. So if I am to draw vertical lines for you to see it. So ito, yan. And let's say ito, this one. So its theoretical cut point should be at this location. So theoretical cut point, laser, it should be at this location or at this point. And it should be at this point. It's just that we have extended this. So this is to be for your extension. Sorry. And this is to be for your extension. Okay, so once again, what we will be doing is that we will be solving for this value. So let's say that this is to be for the value for your x. So x1. Okay, so now how can we solve for the value for your x1? So we can solve for it using plenty of ways. But since this is to be theoretical, let us solve for it using the principles of strength of materials or the mechanics of deformable bodies. So with that, guys, I will be getting the moment equation. Okay, so if this is to be our section, so let's say that this is to be our moment diagram. Of course, it resulted with, of course, your load diagram. Oops, sorry. So for its load diagram, so let's say that this is to be, its beam. And from this beam, guys, okay, so ano pala guys, ito, ikakat ko to, itong portion na to. So I will just be cutting this and I will be redrawing it here. So with that, so this is to be once again the moment. So we have a moment here. And since this is to be a negative moment, so let's say that this is to be it. So this is to be a negative moment here. Since we are analyzing from right to left. So guys, before proceeding, you must review your strength of materials or your mechanics of deformable bodies so that you can understand this section or this procedure. Okay, anyway. So aside from this one having its moments, of course, it would also have its vertical reaction. So may vertical reaction din sa part na yan, hindi lang moment. And its vertical reaction is to be given by this shear, 169.2. So this is to be its reaction, and this reaction here was already solved before, which is for your shear. So with that, oops, sorry. So with that, ito na ngayon yung reaction niya at this portion, and you have, of course, your vertical reaction here. And aside from those guys, you also have your uniformly distributed load as given by the problem. So this was the loading that we have solved for before. And for your W, it would be this uniformly distributed load. So W is equal to 56.4 kilonewton. And we also have a shear here. So this is to be for your shear. Let's say V at X. And also you have a moment here at this portion. Actually, at this portion, the moment should be 0 already. So 0 nga pala to. By the way, the one that we are solving for actually is to be the location here. What is to be this location? For the theoretical cut point for your bars L. So with that, guys, I will be cutting our section to this point only. So with that, so I will be cutting it here. So I will be erasing this part of our section here. And I will be stopping here. Okay. So with that, guys, so we already have our Vx here. So let's say that this is to be for your shear X. And we have a moment. So our moment here, since as you can see, this moment is to be a negative moment, it means that it would be having the same direction as with this. So with that, guys, this is to be the negative moment. So M, let's say L. So this is to be the moment for, the moment capacity of bars L. So now, what is to be the moment here? So still, we do not know that yet. So di pa natin alam kung ano tong moment na to. So the first thing that we will be solving for here is to be what is to be the moment here. So with that, guys, since we already have our section and our section is to be this one, since this is to be our section, what we will be doing is that we will be checking the moment capacity of the section if we would now be removing bars L. So once again, guys, if we would be removing bars L at this point, from this portion up until this portion, it will only be supported by bars M, which is to be the green. So kung nakita nyo, naalis yung bars M dito theoretically, and ang natira na lang at this portion is to be for your bars M. So with that, guys, I will now be checking the moment capacity of the section if bars L is to be already removed. So alisin natin yung bars L. Ngayon, check natin yung capacity ng bars M. So we will now be checking the capacity of the bars M. And that is to be the location here. So basically, guys, what we are doing here is that we are searching for the location in the beam where bars L is not needed. So in Filipino, hanapin natin ngayon aling part dito sa section natin, yung hindi na natin kailangan si bars L. So, ayun. And with that, okay, so going back here, kalimutan ko kasi yung section property natin. So, our section property is to be 300 mm. So, I will just be copying all of this to the analysis part. Okay, so I will just be deleting this already. And, ayun. Mag-solve tayo ngayon. So once again, our goal is for us to know what this moment is. Yun na lang, pangalan na natin MM. So let's say the moment at M or the theoretical moment at M. Whereas your AS is to be for the AS for your bars M. So, ulitin ko lang, ang AS na lang natin ngayon is just to be for your bars M. So, we have already removed bars L. So, for our ASM or our still area for M, that is to be, so as you can see, we only have two pieces. So, two pieces. So, 2 times what is to be the bar diameter of one rebar. So, pi over 4 times 20 squared. So, our answer here is to be, so, pi over 4 times 2, times 20 squared times 2. So, our answer here is to be 200 pi. So, 200 pi millimeter squared. So, that is to be for the area for steel for bars M only. Okay, so once again, this is to be an analysis problem. This part of our solution is to be an analysis problem. What we will be doing is that we will be checking for the moment capacity of this section. Na yung inalis na natin si bars L. So, nakailan ulit na ako doon just to be for an emphasis. Okay. So, if this is to be for your stress diagram, so stress diagram, you have here your your tension force or your T, and you also have here your what do you call this, your 0.85 FC prime. So 0.85 FC prime, and this is to be A, and of course you have your B, and this is to be for your AS FY. So FY automatic yan, guys. So you will not need to you will not need to check if this is to be FS or FY, because we have already designed this properly before, and in our design we have designed it not under compression controlled. So kapag di siya compression controlled, automatic FY yan. Actually, our section here was designed as attention controlled. Thus, once again, automatic FY. Okay, so what is to be the value for your A here? So summation forces vertical. So ayun, equating the forces going towards the right and going towards the left. So for the forces going towards the right, solve for A. So why are we solving for A? Para ma-solve natin yung moment, because your moment is to be equal to, let's say, 0.85 FC prime A B times D minus A over 2, or M is to be equal to ASFY times D minus A over 2. And as you can see, the only one missing here is to be A. So all of them are already known. So with that, guys, I will now be solving for A. So solve for A, and that is to be 0.85 FC prime 28 times A. So A times B. What is to be our B? That is to be 300 mm. So 0.85 FC prime AB. So this is to be equal to ASFY. So our AS is to be 200 pi. So 200 pi times FY, and our FY is to be 420. So guys, basic lang to, no? So 0.85 FC prime AB is equal to ASFY. So you should have already mastered this last prelims. Okay, so moving forward. So solving for the value for your A here. So for the value for your A, this is to be equal to, so 200 times pi times 420 divided by 0.85 times 28 times 300, and our value for our A is to be 36.96 mm. So basically, that is our answer for A, and we can now solve for the value for our moment. But if you want to check if it is, if Fs is to be really equal to Fy, so let's solve for C. So C is equal to A divided by betas of 1, and this is to be equal to 43.48. And with that, guys, no? So if that is to be 43.48, so for the value for your Fs, I will just be writing them here at the top. So i-erase din lang naman natin yan mamaya. So 600 minus D minus C divided by C. So your Fs is to be equal to, so 600 times D. So our D is equal to 440. So minus C, and that is to be 43.48 divided by 43.48. So as you can see, that is to be 5,471. And it is to be a lot greater than Fy. So 420. So, yan. Actually, di naman kailangan talaga ito. It's just that I have solved for it for me to prove that it is really Fy, not Fs. Okay, so with this, guys, so since we already have the value for our A, we can now solve for the value for the moment capacity of bars M. So, with that, guys, I will just be using this equation. ASFy times D minus A over 2. And this is now to be equal to, so our AS is to be equal to 200 times pi times Fy, what is to be Fy, that is to be 420, times D minus A over 2, so our D is to be equal to 440, minus A over 2, so 36.92 divided by 2. So 200 pi times 420 times D minus, so I should say minus, so D minus A over 2, so 440 minus 36.92 divided by 2, answer. So I will just be dividing this by 10 raised to 6 for me to convert it already to kilonewton meter. So this is now to be 111.24 kilonewton meter. So this is to be the moment capacity of bars M. So that is to be the moment capacity if we would now be removing bars L. So with that, guys, so going back here, so it means that this moment here is to be 111.24. So with that, guys, you can now solve for this x. So let's say that this is to be for the value for your x. And using this moment, solve for x. So just like what I have said earlier, that you can solve for it using any method that you know. But since this is to be a theoretical subject, so I will be teaching you on how you would be getting the value for your x using theory or strength of materials or mechanics of deformable bodies. And since you are already in reinforced concrete, you should have already mastered it. So consider this as a review. So among all procedures, I will be making use of this loading diagram. So with that, guys, I will be getting the moment at this point. So let's say that that is to be ML or MM pala, MM. So MM. Sorry. So with that, guys, so I will be once again moving this to the other side so that I would be having space. So the summation of moment at M should be equal to negative 111.24. So why negative? Well, basically it is here. So negative 111.24 kilonewton meter. And as you can see, if this is to be negative, so kapag ito negative yung yung counterclockwise, it means that clockwise is to be positive. So kung nalito kayo dun, just take this into consideration that if you would be getting the moment at that point, it should be equal to mm. So yun lang yun. Basta as long as you know the principle, you do not actually need to memorize this as long as you know which direction that you are going and as long as you wouldn't be having a negative value of an answer. Okay, so let's just solve for it. So negative 111.24 kilonewton meter. So this should be equal to, so wala na naman tayong space. Teka nga, I'll just be moving all of this to the left. Okay, so this is to be for the value for your moment. This is equal to, so let's get the moment here. So take note that this is to be x. So for the shear or the support, that is to be 169.2. So positive 169.2 kilonewton times the lever arm, and the lever arm is X. So times X. So plus or minus. So let's say um, minus. So since I am considering clockwise positive, so as you can see that um, this is positive because if this is to be your rotation point, this shear force would give you a clockwise moment. And as for the loading here or the moment here, that is to be 56.4, or just get the resultant of 56.4 times the lever arm. So with that, guys, 56.4, since this is to be a line load or a uniformly distributed load, multiply this by the total length, and that is to be X. So times X. So with that, guys, you now have, oops, sorry. So with that, guys, you now have a resultant here. So the resultant will be located at, of course, the middle here. So that is to be the resultant, and if that is to be the resultant, the lever arm is now to be equal to X over 2. So times X over 2. So you should have already mastered this in your mechanics of deformable bodies. So simplifying this is now to be equal to X squared over 2. Okay, so that is for this part. And what about for the moment? So for your moment, this is also negative because it is directed counterclockwise. So negative 126.9 kilonewton meter. So you do not need any lever arm here because this is already moment. So ayun. So simplifying this equation, guys. So if that is to be your equation, I will now be putting all of them to the left side. So with that, guys, so this is to be negative 111.24 kilonewton meter. So if I am to put this to the other side, so this is to be negative 169.2x. Then as for this is now to be positive 56.4 divided by 2 x squared. And as for this is to be positive 126.9. So is equal to 0. So simplifying this equation, this is to be a quadratic equation actually. So 56.4 divided by 2. So this is to be 28.2x squared. So I just simplified this. So minus 169.2x. So, and as for this, I can actually combine both of these terms. So 126.9 minus 111.24. This is to be positive 15.66 equal to 0. Okay, and since this is to be a quadratic equation, you can solve for it using plenty of methods. So you can use quadratic formula. You can use mode 3-2, or you can use shift solve. So theoretically speaking, you must solve for it via quadratic equation. But let us use technology to our advantage right now. So in that case, guys, I will be making use of mode 3-2. So not mode 3-2, mode 5-3, I should say. So mode 5-3. So with that, 28.2, negative 169.2, and 15.66. So we should have two answers here. So for the first answer, this is to be 5.906. And the second answer is to be 0.094 mm. I mean meters, I should say. So meters and meters. Okay, since we have two answers, what is to be the answer here? So if we would be going back to this diagram, if ln is to be 6 meters, and our answer, so looking at the calculator once again, our answer is to be 5.906, and for our x2 that is to be 0.094, what this means is that if you would be making use of this x, your location would now be theoretically here. So that is to be the distance now because your ln is to be 6 meters. So it means that 5.906 is to be located here. And as for 0.094, it is now to be located at this port at this portion or at this part here. So 0.094. So with that, guys, it is logical for us to say that our answer here is to be 0.094. Okay. So moving forward once again. So since this is to be our answer already, which is 0.094, it means that this x, or the theoretical cut point of our bars L, is to be 0.094 meters or 94 mm at this portion. And for our extension once again, so teka, sulat ko na nandito no, para mas ma-visualize nyo. So this is to be 0.094 up until this theoretical cutoff point. And with the extension, this might be the greater of your D or your 12 dB. So for your D, that is to be 440 as given by the problem. So this is to be your effective depth. And for your 12 dB, 12, looking at the calculator, so 12 times the bar diameter, and our bar diameter is to be 20. So there. Okay, so with that, guys, this is to be equal to 240 mm. And 240 mm is to be 0.24. As well as for your D, so your D is to be 0.44. And since the greater value here is to be D, so we will be making use of D. So with that, guys, so for the development length required, so LD of bars L, that is to be 0.094 plus 0.44. So with that, 0.94 plus 0.094 plus 0.44, this is to be equal to 0.534. Okay, so basically that is to be the answer here. 0.534. So yan yung answer natin for the development length for bars L. But do not forget, guys, about the minimum LD that we have solved for earlier. So we have solved that the minimum LD is to be 982.71, is to be less than 982.71 mm, or let's say, once again, it is to be less than, teka, erase ko muna tong circle. Since it is to be less than 982.71 mm or 0.982, so for the consistency of the units, so 0.982 meters, we will now be making use of this. So baliwala ito. So we will now be making use of this development length. So from this point up until, of course, 0.982. So ito yung gagamitin natin. Okay, so that is for your bars L. But what about for your bars M? So in actuality, guys, so if this is to be your section, so once again, this is to be for your bars L, and this is to be for your bars M. In actual construction practices and according to the requirement in SMRF, you must provide 2 rebars at the top and 2 rebars at the bottom throughout. So basically, guys, you do not need, in actuality, you do not need to solve for this cutoff point any longer or this development length, since dalawang piraso lang naman yan, so 2 pieces. And with that, guys, in actual practices, once again, the bars M here should be true and true. So the bars M should be from here up until, well, throughout. Because that is just 2 pieces. So 2 pieces lang yan. So let's say that you will be solving for, let's say, the development length of bars that would have, let's say, plenty of free bars. So let's say 8 pieces of free bars. Well, basically, that is to be the part wherein you would now be solving for these bars M. But, ayun. So, for theory-wise, so just for you to know how to solve for this, bars E. So, let us just solve for it. Okay, so let us now solve for what is to be the theoretical cutoff point of bars L. So what we will be, I mean bars M. So what we will be doing is that we will now be solving for this length. So solve natin yung buong yan. So how can we do that? So same procedure. Same procedure here. So just move this to the right. So lakihan natin ngayon yung section natin. So let's say that this is to be our section. I mean our beam up until this point where the moment is to be equal to 0 or the point of inflection. Okay. So there guys. So we will now be solving for the location here. So this location or this portion or the point of inflection, the point of inflection, the moment here is to be equal to 0. So meaning whatever moment that you will be solving for here, this is to be equal to 0. So with that guys, just get this portion here, get the summation of moments horizontal or vertical or whatsoever. So let's say that I will be getting the summation of summation of moment pala. Pag moment, clockwise or counterclockwise. So let's say that the summation of clockwise moment is to be equal to the summation of moment is equal to 0 and clockwise is still to be positive. So with that guys, so negative 126.9 kilonewton meter. So plus 169.2 kilonewtons times x minus, so 56.4. So this is for the uniformly distributed load. 56.4 times x squared divided by 2. So this is to be equal to 0 kasi nga 0 yung moment yan. And simplifying this, so this is to be equal to, so same sa kanina, so 56.4 divided by 2. So this is to be negative 28.2 x squared plus 169.2x minus 126.9 is equal to 0. And this is once again a quadratic equation. And I would be making use of mode 5.3. So negative 28.2, positive 169.2, and negative 126.9. So if you do not have this function in your calculator, you can use the quadratic equation or shift solve. Just take note that if you are to if you are to solve for it via shift solve, take into consideration that you will be having two answers. So getting the answer here. So x1 is equal to 5.121 and x2 is to be equal to 0.879. Okay, and choose this value. Choose the smaller one. Okay, so if you are to solve for it via shift solve, so negative 28.2 times x squared plus 169.2 times x alpha x minus 126.9 is equal to 0. Then shift solve. Then I will be pressing 0 here. So the first answer is to be 0.8787. And for the other answer, so shift solve once again and try to type a higher number, let's say 1,000 or let's say 10. So our answer is to be 5.121. But, ayun. So once again, our answer here is to be 0.879 meters. So with that, guys, if this is to be 0.879 meters, so this portion here, this is to be 0.879 meters. for the development length of bars M, this is to be equal to 0.879 plus the extension, and this is to be the extension. So for the extension, same old, it is to be the greater of D, 12 dB, but we would be adding another one here. So ln over 16, if I'm not mistaken. So check na naman natin yung code. Yes, ln over 16. So that is for your bars M. So ln over 16. So with that, guys, so ln, what is to be our ln? That is to be 6 meters, I think. Yes, so 6 meters. So lnr is to be equal to 16. So with that, so 16, 6 meters, I should say. So 6,000 divided by 16, that is to be 375. So same old, we will be making use of 440. So this is to be 440. So with that, our LDM is to be 0.879 plus 0.44. So this is now to be equal to 1.319 meters. So this is to be your LDM. So if you are to round this up, so you can actually use 1.320 in actual practices, or 1.325, as long as this is to be the minimum. And speaking of minimum, let us check if this is to be greater than the minimum. So sabi yung minimum natin. So yung minimum natin is to be So our minimum here is to be 982.71. And as you can see, 1.319 meters is to be greater than 982.71. So meaning, in this case, theoretically, we will now be making use of 1.32. So 1.32 is to be our development length for this negative value. Okay, but once again, that is to be the theoretical approach. But the thing is, since our bars M is just to be 2 bars, since 2 bars lang siya, in actual practices, you will not be making use of this kasi true and true siya. Once again, theoretically, if this is to be our section, once again, sorry. So if this is to be our section, theoretically, for your bars M, it should be cutted here. So this is for your bars M, and that is to be 1.319 meters, theoretically. But in actual practices, since this is just to be, since bars M is to be 2 pieces only, that should be true and true. So true and true dapat yan. So ayun. So that is for the, what you call this? So that is for the development length for the tension rebars for, well, negative moments. Okay. So I will be providing a separate video for the other provisions, such as for your LDH